Assalamualaikum. Assalamualaikum warahmatullahi wabarakatuh. Good morning, good evening, good afternoon, or good night, depending on what time you are watching this. First and foremost, allow me to introduce myself. My name is Muhamad Fadel Johar with the student ID I0125087. In this instance, I would like to explain my paper with the title of Application of Multivariable Calculus and Partial Differential Equations in Modeling Fluid Velocity in Dam Seepage Flow. Now, why did I choose this title? There are two main reasons why I chose this title. The first one is the importance of dams in the everlastment of humankind. As we know, dams help us to regulate water, store water. They help with flood control. They also provide the chance to gain hydropower energy, and they also help with irrigating our farms. And the second reason is other studies with similar titles normally use more complex equations, such as examples of finite element method or physics-based models that at times can be much more difficult to understand. So my hopes in making this paper is that many more people will more clearly understand the importance and equations derived from for calculating dam seepage flow. So without further ado, we will move on to the methodology part because that is the main part of this paper. This study focuses on seepage flow through a dam structure by modeling the movement of water within a porous media. The system represents seepage flow that occurs due to the difference of hydraulic heat between upstream and downstream regions. The primary objective is determining spatial distribution of the hydraulic heat and evaluate the resulting seepage velocity. Seepage flow is determined by pressure and elevation that differs throughout the three-dimensional plane, causing water to move through soil or rock materials. Thus, a mathematical framework is needed to accurately describe this system. There are several governing equations used here. The equation of seepage flow is based on Darcy's law, which describes the relationship between fluid velocity and the hydraulic gradient within a porous medium. In the form of a vector, Darcy's law is written as vector equals negative of the hydraulic conductivity multiplied by the derivative of the function h. This equation shows that the water flows in the direction of decreasing hydraulic heat, and that the magnitude of velocity depends on both the hydraulic conductivity of the medium and the spatial rate of change of the hydraulic heat itself. The hydraulic heat is defined as the sum of elevation heat and pressure heat, or it can be written as H equals elevation plus pressure over density multiplied by the gravitational acceleration. Here, the function of h is the model of the seepage flow itself. Since hydraulic heat varies in space, it is treated as a multivariable function of h, where h will equal to x, y, and z, which the gradient of is obtained by the implementation of partial derivatives. To ensure the conservation of mass, Darcy's law is used with the continuity equation, creating another governing equation for seepage flow. Specifically, for steady-state conditions in a homogeneous and isotropic medium, this can be written as the second-order derivation of the function h, which will equal to 0. This equation, which is more commonly known as the Laplace equation, describes how hydraulic heat varies in three-dimensional space under steady-state conditions. Each term represents the curvature of each dimension in the x, y, and z directions respectively. The sum equating to 0 means that there are no internal sinks within the system, or in simpler terms, the flow is equilibrium. Physically, this implies that any point within the system is influenced by every other surrounding points, maintaining a smooth and continuous distribution. Therefore, these equations form the foundation for analyzing seepage flow behavior and predicting it accurately. Boundary conditions. Because every single situation is unique and different to one another, we can't just use the same model for every single one. Thus, we need boundary conditions. As explained here, boundary conditions are needed to correctly represent these differences. The upstream boundary is defined by a constant hydraulic heat corresponding to the reservoir of the water level, while the downstream boundary is from the lower heat value, representing the discharge and impermeable boundaries, such as the bedrock layers or cutoff walls, are modeled using a no-flow condition, which can be written as the derivative of the function h over the derivative of the normal force equals 0. This equation ensures that the model accurately represents the interaction between the fluid and the dam structure. The approach we will take is we will use the governing equations to determine the distribution of hydraulic heat within the region. Numerical methods such as the finite element method, or FEM for short, are more commonly used to define complex regions instead of simple geometrics. The analysis focuses on determining the hydraulic heat distribution, direction, and the magnitude of seepage velocity, and also areas with high hydraulic gradients. These results are used to evaluate the seepage flow behavior and hopefully identify zones or areas that has a higher chance for instability. However, we will have several assumptions just to make the equations used much more simpler, because we are not trying to accurately predict real-life occurrences, but we are trying to understand the overall flow behavior of seepage flow itself. So to simplify the analysis, the following assumptions are made. First, the flow is steady state. Second, the fluid is incompressible. Third, the porous medium is homogeneous and isotropic. Fourth, the flow conditions satisfy Darcy's law. And finally, temperature effects and chemical interactions are ignored. By using these assumptions, we can create a much more simplified equation that hopefully still shows the overall behavior of seepage flow itself. For the model parameter part, it's just explaining what each symbol explains. Now we move over to the case study and application of these equations. We will use a very simplified three-dimensional seepage model where the hydraulic heat is defined as 10 minus x minus 2y minus 3z. This function represents a spatial variation of hydraulic heat, where the head heat decreases along the x, y, and z directions. Since it has multiple variables, its variation is analyzed using partial derivatives. Here we have the derivative of h, which then equals to x becoming minus 1, y becoming minus 2, and z becoming minus 3. Using Darcy's law, and by assuming hydraulic conductivity as a constant, in which K, or the hydraulic conductivity, is equal to 1 multiplied by 10 to the power of minus 4 meters per second, the seepage velocity can be calculated as such. And we can approximate that the seepage velocity is roughly around 3.74 multiplied by 10 to the power of -4 meters per second. The result shows that seepage flow occurs in 3 dimensions, with the largest velocity components is in the z direction, which is shown over here. -1 being x, -2 being y, and -3 being z. In which z is also the steepest hydraulic gradient. Additionally, the hydraulic heat also satisfies the Laplace equation, where all the second-order derivatives equate to 0. Here we can see this function when we put it through a second order of derivation. As we can see, this is the first order, and if we put it through a second order, it will all equate to 0. This confirms that the model we used, the H model here, is a valid steady-state seepage flow condition. This proves that by using multivariable calculus and partial derivatives, we can find the seepage velocity and its hydraulic gradients. The solution of the governing equation shows that the hydraulic heat varies continuously within the region, decreasing from the upstream boundary to the downstream boundary. This smooth distribution is consistent with steady-state seepage flow behavior in previous studies done by using FEM or physics-based models. By not having abrupt changes within this distribution, further validates the Laplace equation implemented in the study, where flow is equilibrium and no internal sinks are present. Based on Darcy's law, seepage velocity is directly related to the hydraulic gradient. The results show that velocity increases in regions with steeper gradients. In the example before, the steepest gradient was the z gradient, which was the highest one, where the velocity was the highest. This means that water flows faster where the change in hydraulic heat is more clearly shown. In 3-dimensional conditions, the velocity vector has 3 components of direction. This confirms that seepage flow follows the direction of the steepest decrease in hydraulic heat, rather than just a straight path, which is consistent with porous media flow behavior described in recent studies as well. The analysis shows that hydraulic gradients are not uniform throughout a region. Areas with high gradients represent areas that are more prone to piping and internal erosion, which are widely recognized as key factors affecting the stability of a dam. Overall, the results demonstrate that multivariable calculus and partial differential equations prove as an effective framework for modeling seepage flow within dam structures. Simpler assumptions used in this study limit the accuracy of the models. However, the analysis still captures the fundamental behavior of seepage flow and align with modern numerical and computational studies. So basically, even by using a much more simpler equation, the results are still similar to ones that use FEM or physics-based models, in which what we are viewing is only the behavior of the seepage flow itself, not trying to accurately predict what would happen in real life. So in conclusion, this study examined seepage flow within a dam using multivariable calculus and partial differential equations. The results show that hydraulic heat decreases from upstream to downstream, while seepage velocity depends on the hydraulic gradient and the material permeability. The analysis also shows that seepage flow occurs in all 3 dimensions and that areas with high hydraulic gradients may be more prone to instability. Overall, the mathematical model provides a clear and effective framework for understanding seepage behavior. Some recommendations I have for future researches. Future work should use more numerical methods, such as FEM, to model more complex conditions, including heterogeneous materials and transient flow. They should implement real field data and also implement seepage-related failure mechanisms, as it would hopefully improve the accuracy and practical application of the analysis. This is the results of putting my paper in Turnitin, which is widely used to check for AI or plagiarism. As we can see here, it is completely human. No part was made by AI whatsoever. It even says here AI probability 0%. That's very important. So, yes, that is it. Thank you for listening. I hope that my explanation was clear and easy to understand. Wassalamualaikum warahmatullahi wabarakatuh.